when you guys did the revolutions around axes and try to visualize the volumes, you guys have started to visualize things in 3D. And so this class is all about higher dimensions. It's called multidimensional calculus. We are going to talk about stuff in 3 dimensions, but we can also discuss things in higher dimensions or things that we're not going to be able to visualize. But for those that we can visualize, for those things that we can, I encourage you being able to draw or put in the computer. And Desmos doesn't do 3D, so we're going to have to up our game a little bit and switch to another program that does 3-dimensional stuff. So anyways, let's start with looking at some notation. R is going to be the set of real numbers, which we're already familiar with, but just to let you know, that's the symbol that they use. They say R. And then when we start going into higher dimensions, well, just 2 dimensions, we say R2. We don't say R squared, just the notation, we just say R2. When we see something that's squared like x squared, we don't say x2, we say x squared. But this is not being squared, technically. So this is going to be the 2-dimensional plane, if you want to call it that way. And usually the variables that we use are x and y to represent our things in 2 dimensions. It doesn't have to be x and y. It could be other variables. Later on, we'll see a relationship between x and y in another 2-dimensional plane, and so we'll call it u and v or something else. But in terms of what we're familiar with, we just call it the xy plane. And then if you're talking about things in 3 dimensions, we usually denote it by R3. So again, we say R2, R3, and we don't say R squared, R cubed to represent our different spaces that we're going to look at. Okay, so when we're looking at 3-dimensional space, we also want to look at or try to represent it with a drawing. And we usually represent it with a drawing that kind of looks like this. It's a 3-dimensional space with perspective. So we're looking at 3-dimensional representation in 2 dimensions, and we were pretending that the y and the z axis are actually on the page, and we're pretending that the x is coming right at you out of the page to get your 3rd dimension. And we usually just point to the positive parts of x, y, z. Just like in 2D, we tend to, or at least I just tend to put arrows on the positive parts of x and positive parts of y. We have the positive parts of x, y, z pointing in the directions that the arrows are pointing. Now in R2, we have what we call quadrants. And don't know how important the other quadrants are, but the most important quadrant is where everything is positive. X and y are positive, so that's the first quadrant. Now, if you're looking at something in 3 dimensions, then you're not dealing with 4 things anymore. How many are you dealing with? 4 plus 4. There's 8 of them because you take your z component and you break that to positive and negative, and so you double. We have 8 quadrants. For I guess we wouldn't call it quadrants, we'd call it octants, right? You could try to figure out what the other octants are, but the most important octant and the one octant that we usually refer to in the homework problems and such are the first octant, is the first octant. The first octant is the space, so the part of the space where everything is positive. So that's when x is equal to 0, y is equal to 0, and z is equal to 0. And so these octants are broken up, just like the quadrants, they're broken up by the axes. These octants are broken up by what's called coordinate planes. And so there are 3 coordinate planes, and we can look at it from the positive portion or just all in all portion. But if we look at it just from the positive side, when I draw these planes, just imagine these planes as extending to forever. But let's start with the XY plane. And I would draw it like this. And when you draw things, just I don't know if you guys ever took drawing lessons, but when you draw things in 3 dimensions, you're trying to do 3-dimensional representation. The idea of parallel lines are important. And so this plane, I want to represent this plane as something that's on the XY. And so anything I do should be parallel to the XY axes. And right now we're looking at this plane. It's just happening in the first octant, first quadrant, but technically, it goes on forever. And if I want to make it go on forever, I can try to represent it with more parallel lines. Okay. You guys going to be drawing experts by the end of class? It's not just a math class, it's a drawing class too. All right, so we have the XY plane. We call it the XY plane because it's on the X and Y axes. But the equation of the XY plane, I don't know if it's odd or strange, but the equation of XY plane is actually given by the Z axis. It's all the points in space that have Z's equal to 0. So when you say Z is equal to 0, there is no X and Y dependence on that surface of that statement, Z is equal to 0, does not say anything about X and Y. So you can say, what if I let X equal to 5 and Y equal to 7? Z is still going to equal to 0, right? And so where is that? That's going to be the whole XY plane. So your equation is going to be Z is equal to 0. That will represent the XY plane. Okay? Now, when X is equal to 0, what do you think that's going to be? It's the YZ plane, right? It's the other variables plane. So how would we draw that? Taking advantage of how your eye views things in 2 dimensions, you're going to draw parallel lines that are parallel to the X and the Z, or the Y and the Z. And so if I draw a line parallel to the Y and the Z, I would have something like this. This could be the representation in the first octant. And if I want to extend that, I can extend it out. Again, drawing parallel lines is your key. You can kind of define an intersection here where the YZ plane intersects the XY plane. And the equation, again, is X is equal to 0. Okay? All right, now the last plane is going to be the plane when y is equal to 0. And so when y is equal to 0, it's the other two variables. That's the x and the z. So it's the xz plane or zx plane. And so for that, again, using parallel lines, draw a line that's parallel to the x-axis and parallel to the z-axis. And then you can extend that as well. Okay. Any questions? All right. So again, the first octant is when everything's positive. You can think about the second, third, fourth octant as like the quadrants, and just having z positive. And then the fifth, sixth, seventh, and eighth octants would be when z is negative in the same order. Can you picture that? All right. That's the fifth octant would be right below the first octant. So it'll be the same numbering system as the quadrants, except when z is negative, it'll be 5, 6, 7, 8. Oops, 5, 6, 7, 8. Right? So again, Joseph C are in what octant? The fifth octant. Okay? Everything up on top. Everything up on top would be first. Where's the second? Am I in the second? Okay, first, second, third, and fourth octave above, right? And down below would be the fifth, and that would be in the sixth octave, the seventh, and then the eighth. So that's how we break octaves down. Okay? All right, now let's figure out how to find some points, and then, I'm sorry, can I keep you guys there a little bit more? Not that you can say no, right? All right. Can I have 4 volunteers? You guys will just tell me your hand. You're A. Can I have another volunteer? I need 3 more. All right. Casey, right? Miguel. 2 more. Okay. Johan. So you're A, Miguel, you're B, you're C, and then 1 more. Okay. So I want you, amongst the axes over there, you guys are representing each of these points. I want you to find your octant and where you should be. So, Casey, raise your hand. A, he's A. Miguel, he's B. Yana, C. And Antonio is D. So they're going to find themselves in whatever octant they're supposed to be in, and maybe you guys can help out. Okay, you guys should try to figure out which octants each of those points are in. Are any of them in the same octant? And do you see what they're doing as they're talking about it? So I saw Shannon and Joseph kind of making a motion about taking steps in some certain directions. Yeah. All right. Are you guys all set? All right. I need somebody to answer it. Nobody up here. I need somebody over here to answer. What octant is A in? Actually, Travis already told me. So Casey's in the 5th octant. How about point B? What octant is Miguel in? 8th octant. So where are you? Okay. Are you in the 8th octant? Is he in the 8th octant? I can't tell anymore. And then Johanna is point C. 6th octant. Is that you in the 6th? Okay. 1, 2, 3. Oh, 1, 2, 4, 5, 6. Okay. And then Antonio, 3rd octant. Z is positive, so just looking at the X and the Y, and X and Y are both negative. Okay? Are we good? Is that all crystal? Fair. All right, guys, thank you. You know what? Can I have the points? Mark yourselves here. Try to draw it. So seeing it visually, I think it's a good thing, and drawing it would be even better if you can draw it in 2 dimensions. So let's start off with A. Casey's going to try to draw his point on my graph here. And then actually, since it's working?
Yeah. I think.
So I don't know if you're able to see them clearly while they're modeling up here. But trying to draw this on a flat 2-dimensional surface is a little trickier.
Yeah.
All right, let's get B up there. Oh, label it. Put A right next to your dot.
Ah, this is hard.
So you can try to draw where the dot is just by counting. I think there can be another way to help out the drawing if you're just drawing points. But we won't be drawing points too much here. But for your own visual help, I think when you're drawing this in 2 dimensions,
Positive is like -2, 1.
imagine how they're going
Oh, this is hard. Yeah, but it's like negative. Yeah, so it's negative, positive, and then down. So like down here. Yeah. I'm not really sure here how to draw mine out. Cause the negative. Okay. So right here. Yeah, because I was thinking I'm back here. No, because this is my x negative direction, and this is the positive direction, and then not to be down, so like about here, right? I think here, like maybe around there. So maybe around there.
Like somewhere in the back.
So what I'll do is I'll just model just like in 2 dimensions, when you try to plot a point, you put the tick marks, but then you kind of, before you used to do tick marks, you used to draw a little rectangle, right? We were in rectangular coordinates. We still are in rectangular coordinates, except it's in 3 dimensions, so these things look more like boxes. So if I were drawing A, I would draw like a box. I would start in the x-axis. I would go 2 units in the x-axis. And then I would move along the y-axis. And then I would go 4 units in the y-axis in the positive direction. And then from there, I would go down 1 unit in the z direction. And I don't know if you guys can see this. I'm going to see if I can draw it out. Wait, there's a box there. See if I can take it out. Oh, I missed the line. There's a box. You moved 2 units, 4 units, and 1 unit down. And this is the box that you would draw in 3 dimensions. Okay? Is that cool? That's your drawing lesson for today. So for those people who said that they can't draw in 3D, I can't either, but look, you can see it, right? There you go. There used to be a class in the business division about visualizing things, and we talked about making that a prerequisite for this class. But it's spatial visualization. I was going to teach that class too, and then I thought, well. In any case, if you are completely having a difficult time trying to visualize things in 3D, you're more than welcome to use 3-dimensional programs. And so there's one cool program. I think if you search CalcPlot 3D, there's a community college in New York that had a grant to write a program that plots things in 3 dimensions. And I've seen this when it first started, and this has improved greatly over the years, and it looks really cool now. So what we've drawn are those planes where z is equal to 0, x equals 0, and y is equal to 0. Then you can easily get those pictures. And remember that the x and y can shift to many different directions. I had Joseph pointing his z-axis downward one time, as long as it still follows the right-hand rule. You can get these graphs going. Okay. So if you feel, you really feel like you can't draw and you're having issues with trying to visualize something, you can jump to this program and teach you how to use it over time. But right now, I used this thing called implicit surface that allows you to find a relationship between x, y, and z in an equation and then draw that out. The z is equal to 0 is actually a special kind of surface. That's a regular function that we're going to study where z is solved for by itself. But the others, x equals 0, y equals 0, are not regular z equals to something function. So I had to use an implicit plot. We'll get to that later. But for now, oops, I forgot to continue recording. Oh, it's recording. Okay, yeah, for now, we can, our first things actually, before we really study more surfaces, is we're going to study vectors. So we talked about coordinate planes, and you can also find planes that are parallel to the coordinate planes. We talked about points and octants and stuff like that, and coordinate planes. And so we can describe other planes like z is equal to 5, z is equal to -2, x is equal to 14. Those are all coordinate planes, or those are all parallel to coordinate planes. Just like when you say x equals 5 and y is equal to 2 in as lines in two dimensions, we can also talk about these as planes, coordinate planes, that are parallel to the coordinate planes. It's like saying parallel to the axis, but so when you say y is equal to 5 or y is equal to -1, you're looking at something parallel to the y is equal to 0 plane. And y is equal to 0 plane is the xz coordinate plane. Okay, so let's say that again. Y is equal to, let's say y is equal to -1. So if I take y is equal to 0, y is equal to -1, it's just going to be another plane that's parallel to the xz plane, except it has a y component of -1. Okay? So those are the rest of the coordinate planes. Remember, we're trying to find or express these things where you have x is by itself and then nothing else is around. There's no other variables around. The y or y is equal to -1, and the x and z are not represented in the equation. So let's take a look at more of those types of relations between x, y, and z that has one other variable missing. So here's a handful of equations to look at, and let's see if we can identify what these equations are or what these surfaces might look like. Let's take a look at the first one. The first one, as we know, is the circle, right? But when you present this as a surface in 3 dimensions in R3, well, you have to think, wow, this should be more than just a circle, because a circle is just happening in 2 dimensions. So this circle is independent of what z is equal to. In other words, when z is equal to 0, I should get a circle. When z is equal to 1, I should get a circle. When z is equal to 15, I should get a circle. What do you think this surface is going to look like in 3 dimensions? It'll be a circle that's been kind of swept up and down, which will give us a cylinder, right? So we can imagine this thing in 2 dimensions. Whoa. It's just a circle if we're looking at it just on the xy plane. But then since z should be included and we're not being specific about what z should be, and there's no other relationship, then it should just go up and down as a circle. The same way for the second graph. What do you think that graph's going to look like? That's another cylinder. But this time I would draw my quote unquote circle on the YZ plane. So on the YZ plane, I would have a circle. And then I would take that circle and sweep it along the x-axis because this is independent of what x is equal to. So now I have a cylinder going along the x-axis. Okay? And again, taking advantage of our graphing program, let's take a look at something like that. Where we have y squared plus z squared is equal to 1. Just like we anticipated, flat on the xy or flat on the yz plane, it looks like it's just a circle. And then coming right at you along the x-axis is a cylinder. Okay? So that's the general story when we're talking about things where a relationship between x, y, and z that we're expecting to be in R3 where one of the variables is missing. So if we take a look at x is equal to z squared, what do you think that's going to look like? Half pipe? Say you were drawing this in 2 dimensions like I'm about to. Kind of, but it's not. It's being revolved around somewhere. Yeah, maybe. So I would first look on the xz plane. So my xz plane. And I would draw, it looks like x is equal to z squared. It's a parabola. Now I have to determine if it's opening up, down, left, right with respect to x and z. And so with that, you have to, good thing we're all experts with conic sections already. Z is being squared. X is the other variable. Which way is it opening? To the, let's say, which axis is it opening towards? The positive x, the positive z, or the negative x or negative z? Positive x. It's opening up positive x. So if I were to draw this flat on just the xz plane, if I were to just cut out the y, forget about the y, and I just look at this on the xz plane, I would say my z is being squared, right? So that's like the independent variable, and I would be opening up along the x-axis. So that's what my conic section lessons, that's what my conic section teacher told me. That would be me last week. So if you look at it in 3 dimensions now, it's opening up towards the x-axis, right? And as it's opening up towards the x-axis, it's flat on the xz plane. And now comes the sweep. We're going to take this shape and sweep it along the variable that's not included, which is the y. All right, I really messed that one up. I hope you drew it better than I did, but I'm just going to use the program to graph it anyways. So with a graphing program like this, you can take the view from different angles to make sure you, so my drawing just went like this, whatever that is. It's hard to see, but if you look at it from a different point of view, what? I'm not able to turn now. There we go. There's that parabola opening up towards the x-axis like we drew in 2 dimensions. Or I guess we should look at it from this way because that's when x is positive. Ooh, that's big. And then you can try to find a nice 3-dimensional viewpoint that would work for us. Maybe that. All right. How do you think the graph of the last one's going to look like? It's x times z is equal to 1. You probably have to know what the graph looks like first. What? How would it look like on the xz plane, I guess, is the first thing that you want to do. Why don't I let you think about that? Kind of, not quite a root function. Some other function. No? All right, I'll let you guys think about that. We have a couple of other things that we want to get through for today, and so maybe your lab assignment tonight will work for us because I expected to get through the second section, but we're not there yet. There's going to be many distance between 2 things that we're going to study, so I'm sorry, I'm going to change this from distance formula, but distance between 2 points formula. Because later on we're going to be looking for distances between 2 planes, between 2 lines, and all kinds of stuff. So in this case, we have a distance between 2 points. If your point is given by x1, y1, z1, and x2, y2, z2, then the distance between those 2 points is going to be this. Now this is similar to, we talked briefly about the distance, the arc length formula, and it has something to do with the distance between 2 points in 2 dimensions. But here we have the distance between 2 points in 3 dimensions. I mean, if you scratch out this last part, it's really the distance between 2 points in 2 dimensions. So if you have higher dimensions, you can find distances between 2 points in 3 dimensions. Hell, you can even find distance between 2 points in 5 dimensions just by adding more difference between the other components. But imagine if I said, I want to know the set of all points that has a fixed distance between x naught, y naught, z naught, and some other arbitrary points x, y, z. So imagine how you would kind of create this surface looking thing. So let's fix a point x naught, y naught, z naught, and let's fix the distance. You can fix the distance by just looking at a stick. That doesn't change length. So looking at a stick that doesn't change length. And this is fixed. This point is fixed, right? And I want to describe all the points that I could possibly draw with this. If I just look at the endpoint. What is that? It's just a sphere. Okay? If you don't agree, can you ask the question or say why you don't think so? All right, so we'll agree that it's a sphere. So by fixing x naught, y naught, z naught, and the distance d, and actually, what if we change the name d? What other variable do you think I'd want to use? So if your distance was fixed, then that means you can write this expression or this equation where you have a fixed distance, and then you're looking for the distance between x naught, y naught, z naught, and some random point x, y, z. And then you have this relationship between the x, y, z, and x naught, y naught, z naught, and r. And you could probably make it look a little bit nicer by squaring both sides. And by squaring both sides, then we actually get the equation of a sphere. So if you know you're a fixed point, and the fixed point will end up being your center of your sphere, and then you know your radius, then you can express this equation as the equation of the sphere. Okay, and just as an example, since we do have that cool graphing program, let's figure out how this is going to look like. So let's do a center point of 1, 1, 1. So I have x minus 1 quantity squared plus y minus 1 quantity squared plus z minus 1 quantity squared is equal to, let's put a radius of 1 there, And now we have a sphere centered at 1, 1, 1 with radius 1. Okay? All right. Some of the more interesting things we're going to do later on is we're going to take a look at when a sphere or when any surface intersects maybe a plane, like what drawing does it come up with, and a variety of other things. But the first thing for us is to kind of gain confidence and gain control over looking at these surfaces and being able to visualize things in 3 dimensions. Take a picture of that. Are there any questions? So it'd be nice to have a 3-dimensional model. Have a connection with a VR group, virtual reality. Maybe we'll try to play around with that. I have plans to make a 3-dimensional surface. I'll see if that happens. But if nothing else works, at least we'll take a look at how things are drawn out with a computer program like CalcPlot 3D. If you have any other programs that you might have seen before and are interested in using, go ahead and do that or let me know, and then maybe I can show it to the class. But I want you to take advantage of this, try out some things, mess around with the program to see what kinds of things you can draw. There are options for drawing a bunch of things, including points and vectors, which is what we're going to dive into in our next class period. Okay? All right, that's it for today. Wow.